am I on the screen? And a few postdocs. He was a permanent researcher at CNRS here at IAP for 2 years between 2002 and 2004, before leaving for University of British Columbia. He's been working, as you all know, mainly on weak lensing analysis, and was one of the pioneer of the detection of weak lensing. One of the, with of course, sorry. Yeah, but with Yannick Méliès and other people that we know here, such as Francis Bernardo, for example. So first detection of the 2-point function, first detection of the 3-point function a few years later. Many leading role in the CFHT LS analysis. I mean, it's a full career on weak lensing, and lots of pioneering work on the topic. But of course, he's not here to discuss this question. He's also working on lots of other topics. In particular, today he's going to tell us about why is it so difficult to probe the nature of dark matter. Before I leaving to tell us all about that, just to say that if you want to join for lunch, you're welcome, and just ask me at the end of this talk. And also that Ludovic has been visiting CEA and IAP for at least 2 months now. So, you're staying for 2 months. You've been there for 2 months. He's at IAP every Tuesday, and he'll be there until the end of December. So this is a good occasion to discuss with him either weak lensing or nature of dark matter. So please, Ludovic.
Thank you very much. It's great to be here and give a talk here. It's on. Should I move it up? It's fine, you can hear me? Okay. So I have 2 devices, a laser pointer and yeah. All right. Okay. So yeah, I will talk about something that is not initially my research topic, but I switched to, well, not completely, but I'm working on something different. Yes. Yes, it's all good. Which has to do with the nature of dark matter. So there's something people agree with, is that there is dark matter in the universe. There is no doubt about that. There are multiple evidences. The first one 90 years ago. And also something that's not being disputed is the amount of dark matter we have in the universe, roughly 5 times the amount of bionic matter we have, we know of. And something that's still an open question is about the nature of dark matter. Despite 90 years of observation and trying hard to understand the nature of dark matter, we still don't know what it is. I went to the CERN web page, the public page, and searched for what they say about dark matter, and found this code that says dark matter is dark, so it does not absorb, reflect, or emit any light, making it extremely hard to spot. So it's something, maybe I should use that. It's something I would call the dark matter paradigm, in the sense that what the CERN page says is the dark matter is dark, it's non-interacting, and it's made of non-bionic stuff. The first part of my talk is to actually try to deconstruct this idea of dark matter paradigm, because none of this is actually fully supported by observations. And I will show you why in a moment. But of course, people are not stupid, and there is a reason why we have this dark matter paradigm, which is the basis of what we think dark matter is about, and specifically a theoretical motivation, which goes back to the 80s, 90s. Back at the time, people, mostly particle physicists, trying to understand things like the phase transitions in the early universe and particle physics, they realized something quite remarkable, which is that when the universe is going through the electroweak phase transition, so very early universe, there was a potential for creating lots of new particles, especially in the context of supersymmetry at the time, which was also developed, creating lots of particles which happen to have the right mass and the right number density, which leads today to an omega matter, matter mass density of the order of 1. There was absolutely nothing in the particle theory to fine-tune this. This was not a fine-tuning. This was just a pure coincidence. And that's what something was called the WIMPs. So WIMP stands for weakly interacting massive particles. The WIMPs miracle. Miracle in the sense that you have a fantastic theory, particle physics, which predicts something that happens to be true. Omega matter is of the order of 1. So the dark matter paradigm I mentioned before, dark matter is dark, non-interacting, and non-baryoning, completely makes sense in the context of WIMPs. But the thing is, the way it should have been logically is that WIMPs miracle should lead to the dark matter paradigm. But something happened in history that actually the inverted logic happened, that the dark matter paradigm became the basis for everything, and in particular, the dark matter paradigm became the support, the motivation for WIMPs as dark matter. So the reason why this paradigm is not supported by observation, let me go through these arguments. Let's start with the first one. First one that says dark matter is dark. Well, logically, even that statement is a nonsense because it's dark relative to something else. And it depends on your instrument capability, how dark, how deep you can go in observing at certain wavelength. And it depends on the luminosity of the sky at those particular wavelengths. What I'm showing you here is the intensity of the global sky as a function of wavelength from radio to gamma ray. And believe me, I made a calculation. If you assume a completely ridiculous dark matter theory where dark matter is made of Jupiter-sized object at dust temperature 20 K and calculate the flux you would observe from this dark matter, it's way below here, completely undetectable. In other words, the concept of darkness, if you have assumed this kind of dark matter model, is a relative concept. So it is not true that dark matter should be dark. It has to be understood in a certain context. Second point in the dark matter paradigm, dark matter is non-interacting. So what do we mean by that? Non-interaction has to do with interaction rate, which is something we can calculate. So interaction rate of any species goes like the number density of that species times the cross-section of that species, times the relative velocity between two particles of that species, right? So in the context of WIMPs, it was assumed that the cross-section of the dark matter particle is really, really small. If it's really, really small, in order to keep the interaction rate at the same level, you need a very high number density of particles. But the thing is, NX is not unobservable, right? The fact we say NX is high is completely pure speculation. It's not supported by any kind of observation. Let me illustrate what I mean here. This is the solar system, sun at the center. We are here rotating, orbiting around the sun. Imagine WIMPs like dark matter. So WIMPs, typical WIMPs mass, 100 GeV, so 100 times the mass of a proton. You can do the math. It's roughly speaking 1 dark matter particle per cubic meter. One of these particles per cubic meter. So they are actually everywhere. And as we speak, we are crossed by many WIMPs particles at every second. But if instead, all the mass contained in the solar system at any given time, you assume that makes only 1 dark matter object, very high mass object, but just 1. It turns out that the mass we have typically at any given time in the solar system sphere defined by the Earth orbital radius is about 5 times 10 to the 16 gram. So if dark matter is made of objects like this, you have a very high mass particle and an extremely small number density of particles, which already right away completely defeats any attempt at directly detecting them. You would have to wait a ridiculous amount of time until a particle that massive and that rare actually hits your detector. So the concept that the idea that dark matter is non-interacting is actually relying on an assumption which is not based on observations, which is not confirmed by observations. In fact, you can rewrite the interaction rate, like I showed before, Nx sigma x delta V, as sigma x, the cross-section divided by the mass of the dark matter particle times the mass density. Why am I doing this? Because the mass density is actually something we can observe. We actually know the mass density of dark matter around us, and it's approximately 0.3 GeV per cubic centimeter, so a third of a proton mass per cubic centimeter. So that's the only thing we are sure about based on observation. What that means technically is to keep the same interaction rate, you can have dark matter be low mass and very low cross-section, that's the WIMPs, but it could also be very high mass and not so low cross-section, which is many other possibilities. So the fact dark matter is non-interacting, it's a statement based on the assumption cross-section is small, but we have no observational proof that's the case. Just to put some numbers here, because like I said, rho, the mass density for dark matter is something we can observe, the rho x, which means we can constrain the ratio cross-section over mass from observations. You know, if dark matter interacts too often with, say, baryons or photons, we should see a signature at some point. And I'm listing here 3 constraints, fairly recent constraints we have on that ratio, cross-section over mass. If you look at from the distribution of large-scale structure, the constraint we have is that sigma xx, so in dark matter-dark matter interaction over dark matter mass should be less than 0.025 centimeters squared per gram. If you look at the hot gas, temperature of gas in clusters of galaxies, the constraint is a bit better. And if you look at the constraint for the cosmic microwave background, the constraint is even stronger. But yet, these constraints we have from data are very weak. What do I mean by they are weak? They are weak if you compare to what the WIMPs model says about sigma over m. For WIMPs, very small cross-section, well, very, very small cross-section and very small mass, the ratio is 10 minus 20. So you have this range between 10 minus 20 and the lower bound, which the strongest bound, constraining bound we get from the CMB, 10 minus 7, where anything is possible. If you have a dark matter candidate where sigma over m is 10 minus 10, 10 minus 15, it's totally fine. It will totally behave as CDM, and it will not break any observational constraint we have from cosmology. So the last one from the dark matter paradigm, dark matter is non-baryonic. Where is this coming from? Well, you know the answer. It's coming from Big Bang nucleosynthesis. But what does it mean really? So if you look at the energy mass pi for the universe, like I said at the beginning, we know most of matter should be dark matter. And we say it has to be non-baryonic because if it's baryonic, it will mess up with the Big Bang nucleosynthesis. If you put numbers on that, if you assume all matter is actually baryonic, in other words, you turn omega b into 6 times its value, what happens? You can redo the calculation for BBN, and you can show that the deuterium abundance is reduced by factor 20, helium-3 abundance is reduced by factor 2, and you increase the lithium abundance by factor 10. And these changes would massively contradict observations. So this is where the statement dark matter is non-baryonic is coming from. But there is a logical failure in this argument in the sense that I'll show you in a moment. So like just to summarize, BBN implies dark matter cannot be made of baryonic object, but the sentence is missing something, which is if they are made after BBN. Because it means at the time of BBN, they exist as baryons, they would mess up with BBN, and everything I said before would be a problem. So that automatically invalidates non-stellar remnants such as white dwarf neutron stars, stellar black holes, brown dwarfs as dark matter candidates, because they would have been like normal baryons back at the time of nucleosynthesis. But if you can find a process by which dark matter objects are made before BBN from baryons, it's totally fine, because they would not interfere with the Big Bang nucleosynthesis in any way whatsoever, and you will not break this abundance problem I mentioned before. An example of this are primordial black holes, which was a very exciting theory for a long time. It has problems nowadays for different reasons I won't get into, but primordial black holes would essentially form them before BBN. So they would still exist today as primordial black holes, and they would still fly around us, and they would not have not interfered with BBN. I just came across this very nice review of primordial black holes. If you want to know all the ins and outs of primordial black holes, I encourage you to have a look at this paper. Primordial black holes is not topic of my talk today. Topic of my talk is more like the generic objects we named, that those dark matter objects could be made before BBN and could be a lot more massive than elementary particles. Those, they are called macros in the jargon, generally speaking. So first, to answer the question of the title of my talk, why is it so difficult to probe the nature of dark matter? Maybe because we are not looking at the right thing, and maybe because not at the right place either. If we keep constantly thinking that the dark matter paradigm is true, which is not correct, then the only option is indeed to look for particle-like, elementary particle-like dark matter models. But if you accept that the dark matter paradigm is not observationally motivated for the reasons I just said, that opens up a whole range of parameters. So this idea, of course, is not new. It was developed early on. Stephen Hawking with the primordial black hole started this in the 70s. Ed Wheaton and others developed this idea of you could build dark matter objects from standard model of particle physics, which could constitute today's dark matter. Some of them were ruled out for reasons, again, I won't get into, but for some of them actually still survive. And the one I will talk about in the rest of my talk is the axion quark nugget model. This is, of course, not a very popular approach nowadays. As you know, the most popular approach are way beyond the standard model of particle physics, the so-called BSM models. I'm listing a few of them here. Extremely popular at the moment is ultra-light axions, fuzzy dark matter, where dark matter is those gigantic bosonic particles the size of a galaxy. Steroid neutrinos, self-interacting dark matter. I mean, the list is pretty long here. It's okay to look for candidates, but BSM candidates is indeed the only option if you assume that the dark matter paradigm is true. But like I said, it's not observationally motivated. So there is no reason to stick to BSM solutions for the dark matter. And something I also want to add, the non-discovery of WIMPs and the recent lack of BSM physics at the LHC implies logically that in principle, WIMPs should lose their status of premier dark matter candidates for the whole game here. So the point I want to make is if it's still possible to explain dark matter within the standard model or assuming some very little twist to it, then we should try. Because there is no reason to go beyond something that works fine, has proved to be extremely successful. It explains pretty much everything we know in nature. There is no logical reason to just get rid of it entirely. So the standard model, of course, is not perfect. We know it has some issues. And one of them is the so-called strong CP problem, which I'll get into, but a way to solve it is invoking the quantum chromodynamic axiom. And this is the starting point of the AQN story I will tell you about now. I will skip entirely the AQN formation of dark matter. This would be a pure particle physics talk, which would take at least an hour, but we are among astrophysicists here. I want to focus on what exactly should we expect if dark matter is really made of those axion quark nugget objects. The bottom line is the following. There is a process in this model that takes place at the quark-hadron phase transition, which is when neutrons and protons are actually formed from free quark and hadrons. During that process, because of the axion and the way it couples to matter and antimatter, you can grow nuggets, pretty much like you try to make crepes and you fail making the paste and you have those nuggets in it. So you can grow nuggets of matter and antimatter. That happens before matter-antimatter annihilation. So you grow both of them. You grow nuggets of matter, you grow nuggets of antimatter. There is an asymmetry which develops because axion does not couple the same way to matter and antimatter. At the end of the formation process, you get nuggets which are made of matter, essentially quarks, and nuggets made of antimatter, essentially antiquarks. To respect the neutrality of those objects, eventually they will develop an electron sphere for the quark nuggets ones. So the object in principle stays neutral. And the positron sphere, so anti-electron, for the anti-quarks ones. A very easy way to picture what these objects look like, they are like miniature neutron stars. If you are familiar with neutron stars, that's typically what they are. Now, gravity does not hold them, it's the action field, but again, that's a separate story. If you are interested in knowing more the details of this model, I really invite you to look for this paper here. So just to put some numbers, yes, you have those nuggets. Their sigma over mass is very small, 10 minus 10. So it's way below observational limits that I mentioned before we have. It's a lot more than WIMPs. Remember, for WIMPs, it's 10 to minus 20. So this guy is more like 10 minus 10. But it's small enough, makes it fully consistent with CDM, fully consistent with any observational bounds we have. The accurate information process hides baryons before BBN, right? Because it takes place at the quark-hadron phase transition, which is an energy scale of 170 MeV. Remember, BBN takes place at around 1 MeV, approximately. So this is way before. And the typical mass of those things is 10 to the 24 mass, 10 to the 24 times the mass of a proton. There is a mass range. You expect to have a mass function for those things. There is formally no upper bound, although you can think of one, but there is a lower bound because the less massive ones would actually be destroyed during BBN because of annihilation. Again, not messing up with the Big Bang nucleosynthesis. So typical mass for those things is from 1 gram up. 10 to the 24 times mass of a proton is 1 gram. And they have, I think I mentioned this before, they have nuclear density. So what is the size of a 1 gram thing? Nuclear density is about the size of a bacteria. Right. So 10 minus 5 centimeter. So fine, so now we have this object. What does it do, astrophysically speaking? The interesting ones, of course, are the antimatter ones. The matter ones, they are just not doing very interesting things because they don't interact much with the rest of the universe. Antimatter ones, however, occasionally will encounter surrounding material, such as a collision with a proton. Of course, when the proton gets in, eventually it will get annihilated. Annihilation products gives you some heat. Part of this heat will be transferred to the positron sphere of the nugget, which will acquire a larger temperature. So the positron sphere will puff up a little bit and will emit absolutely very classical Bremsstrahlung radiation. So there is an absolutely classical calculation you can do here by how much Bremsstrahlung flux you get from this heating. Typical heating for typical collision rate with protons in the galaxy brings the temperature of the nugget to about 1 eV. Now, sometimes nuggets will eventually cross things like planets, can get much, much higher temperature, but sometimes the nuggets travel in environment with a very small amount of baryons, and temperature could be much less than that. So the temperature of the positron sphere is the important parameter here. A fraction of the energy will escape the system as X-rays, typically in the range of 110 keV. So we have here potentially two very clear, very well identified astrophysical signatures from the existence, potential existence of nuggets, which is a radio emission from the positron sphere and X-ray emission from the hotspot. So I have 3 slides with a bit of formulas, and then we'll go through examples so we know what do we expect to see here. So like I said, the calculation is relatively simple. It's QED, perfectly conventional calculation. The flux at a given frequency nu getting out from the positron sphere, so this Bremsstrahlung flux, is given by this formula here. So there are some things that maybe do not look very conventional to you, but this exponential should look very familiar to you. That's the typical Bremsstrahlung cutoff, exponential cutoff. If you integrate this formula over frequencies, you get a barometric flux from the nugget which is this form here. So this plot shows you typically the flux coming out from the heated positron sphere from a nugget as a function of frequency. And what you should notice here is not much the exponential cutoff, but it's the fact that it's the plateau going towards radio wavelength. That's very important for what comes next. In other words, nugget radiation has a hard spectrum in the radio range, right? Very different from blackbody radiation, where it should drop as nu square in the Rayleigh-Jeans regime of the blackbody radiation. So this is not blackbody radiation. It's pure Bremsstrahlung with absorption taking over at 1 gigahertz or so. So you have this flux, which is this complicated expression here. So what do we do with this? As soon as you have a collision with a proton, right away you have 2 GeV energy available that you can distribute, at different places. Why 2 GeV? A proton is 1 GeV. It's going to annihilate with 1 GeV of material inside the nugget. So you have 2 GeV available. Out of these 2 GeV available, there is a chance that the proton actually does not get annihilated and just bounces off from the nugget. It's called quantum reflection. So that's taken care of by the factor F, which is about 10%. That's, again, calculation you can do. And then once the proton gets in, a fraction of the energy will go to reheating the positron sphere. A fraction of it will escape as those X-rays I mentioned before. The fraction 1 minus G is the one that gets energy transmitted into the positron sphere. That's the one we are interested in. Now, this is the energy available per collision. What about the per unit of time energy injected in the nugget? So you basically take the energy available per collision and you multiply by the collision rate with protons. So you multiply by the number density of baryons you have, n bar. You multiply by the size of the nugget, right? Because it hits material things on the way. And delta V is the relative velocity between nuggets and baryonic matter. So that gives you the power available from this collision. From that, you can literally calculate the nugget temperature. You know how much energy is injected in the nugget per unit of time, but you also know from 2 slides before what the bolometric flux is from the system for a given temperature. So by equating the two, you actually get the temperature of the nugget. Okay? So from that, you get the temperature of the nugget. From the temperature of the nugget, you can go back to the initial flux formula and calculate the total emissivity of the nugget, radiated away from the dark matter baryon collision, which is this expression here. The thing I really want you to notice here is that the emissivity scales like the number density of nuggets times some power of number density of baryons, which is extremely highly non-conventional. Usually people who are looking for a dark matter signature in the electromagnetic spectrum, they make the assumption the signature comes from dark matter collision, for which the emissivity should scale like number density of dark matter square. But it's not the case here because of the nature of the interaction. And because the only way to get a signature from the nugget is by direct interaction between nugget and regular matter. It's actually strongly interacting. So the process to calculate emissivity in any astrophysical context is very simple. You start from your favorite model of baryons. Could be a galaxy, could be the universe as a whole, could be H2 region, whatever. You know the number density of baryons in your system. You need to know the relative velocity between dark matter and baryons. That's this delta V. From that, like I said, you can calculate the temperature of the nugget everywhere. And to that, you add the distribution of baryons, the distribution of nuggets, NAQN. You need to know the mass of the AQN, which is the only free parameter in the model, how massive these things are. Is it 1 gram, 10 gram, 1 kilo, 10 tons? That's open. And by combining this, you get the emissivity. That's the process. It's very simple. Any n-body simulation can do that. So there is one thing I want to mention, maybe if I have time, I'll just quickly elaborate on that at the very end. Heated AQN, like the positron sphere heats up a bit, the least bound positrons will actually escape the system. And there is a simple calculation you can do, a basic argument based on kinetic energy versus rest mass energy. If kinetic energy is too high, it just escapes the system. It's interesting because potentially it makes the nugget ionized. So you have a dark matter that carries an electrical charge, which also potentially could lead to interesting astrophysical signature. But let's keep that on the side for now. So now let's look at what do we expect from this model. Like I said, the calculation is easy. So now let's turn the crank and look at different environments. Let's look at large-scale structures first. So for that, we used a hydro simulation from Klaus Dollach's group, the magneticom simulations. And we used their redshift 0 simulation just to get a first estimate, what signal we expect. Remember, what we need is number density of baryons, number density of AQN, so dark matter, and relative velocity between baryons and dark matter. But all of this is available from the simulation. So NAQN, it's a slice of redshift 0 cube that looks like this. The N bar number density of baryons you get from the simulation is here. Of course, they are very similar. From the simulation, you know the temperature of the gas, the baryon gas. This is important if you want to check whether the environment is ionized or not. That goes back to my previous statement. If the nugget is ionized and travels through an ionized environment as well, interesting thing could happen, right? So yes, the environment is ionized. Turns out it has no impact here because the number density of everything is so low. So in fact, in practice, we don't really care. And that's the delta V. I actually, in passing, I've never seen a plot like this showing the relative velocity between dark matter and baryons at redshift 0. It's interesting, the values you can reach. So you have all the basic ingredients here to calculate the emissivity. And what you get is this. So from that redshift 0 cube, if you put yourself on the side of the cube and observe the cloud and ask yourself, what emissivity should I get from this dark matter, well, nugget gas interaction, this is here. So the units are in what radio people like in Jansky, so Jansky per steradian. That probably tells you nothing to most of you, but it's approximately 10 minus 5 the level of Sonia-Zeldovich amplitude. So it's faint, it's really faint, but keep in mind that it's just redshift 0. This is still work in progress, like looking at the whole line of sight is something we want to do next. And it will only add up to the signal. It will not stay at this level. In terms of detectability, this is the same amplitude as the Riesz-Yama effect. So there is hope that in the future, with future experiments, CMDS4 maybe, I don't know, we could detect Riesz-Yama effect. So potentially this is something that could be at the same level. Maybe I can skip these plots. So moving to higher redshift, interesting epoch for us is also the transition going from dark ages to cosmic dawn. So from the Big Bang to now, we know the universe went through several epochs. Again, there is potentially interesting thing here to look at for a model like the AQN. Especially because the number density of baryons scale 1 plus z cube. And number density of AQN also scales 1 plus z cube. So if you look at things at redshift 100, 200, 300, you get a massive boost factor in your interaction rate. Because again, remember, it goes like NAQN times some power of n bar. Okay, so that's something you can calculate, again, easily. Everything is easy to calculate here. And the result is quite interesting. So if you look at the global emissivity of the sky again, the plot I showed at the beginning, there is this thing on the left here, which shows, so this is called the cosmic radio background, but this is the low frequency one, below 1 gigahertz. It's interesting because there are measurements here, and the measurements are way above blackbody spectrum expected from the CMB. How above? So these are the data points collecting from different experiments back to the 1990s or late 80s. These are data points. The FIRAS measurement of the CMB temperature at fairly high frequency is here. So that's consistent with the CMB temperature today of 2.725 K. Everything is fine. But as you observe things at lower and lower frequency, people noticed that it gets anomalously bright. And these are the data points here. So the units here are brightness, temperature. This is another way of reporting intensity. Brightness, temperature, it's very familiar unit for in radio astronomy. Anyway, the point is, there was a recent measurement from balloon experiment called ARCADE and ARCADE-2, which confirms this exists. So ARCADE data points are right here. So this is absolutely real. What I'm showing you here is absolutely not speculation. And the thing is, this excess is absolutely amazingly uniform across the sky. It's hardly compatible with anything within the galaxy. It's hardly compatible with anything to do with large-scale structure, because there was actually a recent paper showing that the level of isotropy in this emissivity is so great that you can't even make it match with the cosmic infrared background. Well, because in CIB maps, the inhomogeneity would be too great. Now you take the AQN model and try to see what you get from this hard spectrum in a radio. And amazingly, this is the prediction you get. You get the right slope, and you get an amplitude. So of course, the model has still a free parameter, which is the mass of the nugget. So where it falls is open, but the slope is remarkably close to those measurements. So I, of course, do not say this is proof at all, but this is disturbing. Let's move on to the next one. So going beyond the dark ages, we could ask the same question for spectral distortion. So if I go back to this plot here, now we are going before dark ages. We are asked what happens before even recombination, where in principle, nothing can be observed, but that's not actually quite true. So this is the Planck spectrum of the CMB. And as we all know, it's remarkably close to a black body spectrum. In fact, it's so close to a black body spectrum that I can't even draw the error bar on this plot. The CMB is a perfect black body at a precision of 5, 10 minus 5. So if you push the precision beyond that, it's expected that at some point you will see deviation from black body. And the process are well understood. In fact, this is the kind of science that people like Ludovic and Univ started way back in the 70s. Dizotti and many people actually wrote nice theory papers to explain that no, the CMB spectrum is not a pure black body. We expect to see distortions. This has been revived recently with the work by Jens Schluba and others. Why is it interesting? It's interesting because if dark matter somehow interacts with itself or with baryonic stuff, it will inject energy at any given time, even before recombination. So you have this energy injection process that we expect should take place. There is great literature on this. Essentially, what's happening is the following. So if you look at the history of the universe from early on to late, at redshift about 2 million, which is 2 months after the Big Bang. So let me show you this. I should have step-by-step thing. But anyway, at redshift for about 2 months, so redshift 2×10⁶, 2 months after the Big Bang, everything is fully thermalized. So if you have a process that injects energy for whatever reason, the only thing it will do is change the effective temperature of the plasma. It will not distort the spectrum at all whatsoever. The spectrum will still stay perfectly Planckian. But after that redshift, up to recombination, you can have development of distortion because the thermalization simply does not have time to complete. And this is true for the basic collisional processes that explain the CMB spectrum, such as Compton, double Compton, Bremsstrahlung effects. They actually lead to distortions because those processes do not complete the thermalization process. But you also have different physical effects that take place that will also imprint some distortion. And among them is any kind of dark matter signature. So potentially there is actually a very interesting window of opportunity if we could observe the shape of the CMB spectrum to great precision. By great precision, I mean at least 10 to the minus 8 or even better. Potentially we could see all of this. We could see physics before recombination, which in textbook you learn is impossible, but actually it is possible. And dark ages. So what comes after, there is a well-known CMB spectral distortion that you all know of, that's Sonia-Zeldovich. It's low redshift, CMB distortion coming from low redshift. So this plot shows you the status of that field. It shows you a few things. So this one is the CMB spectrum here, well, the measurement. And this one here, so that shows you the SZ spectrum. So the typical transition at 0 and at 217 gigahertz right here. And as you move down, there's more like relativistic correction for Y, new distortion from the signal damping. There was an experiment called Pixie experiment, which was proposed a couple of years ago to try to push the detection limit right here. The proposal was not funded, it was rejected by NASA. I think ESA had something similar, which was also rejected. But what's interesting is the sensitivity level. It's getting very close to Jansky per steradiant. Maybe you don't remember my plot before, so I add this, whoops. I don't know, for some reason it doesn't show, but the AQN signal is exactly sitting right here, that range. So future experiments potentially could directly see an effect of AQN if it's real. Okay, so let's completely change scale and look at local universe, the Milky Way. Beautiful picture of the Milky Way, which combines stars distribution from Gaia and the dust observed from Earth. So there are two things I want to mention to you here. The first one is a study made by WMAP and confirmed by Planck, which is the existence of this haze at virtually all wavelengths, so all frequencies. So in that paper, you can see they were very careful with the making of this haze, starting from the raw map and removing the CMB, removing H alpha contribution, the synchrotron, the dust, and so on and so forth. And you remove all known astrophysical sources, and you end up with something that's called the haze, which cannot be eliminated and has no clear explanation. Yeah. So that's for one thing. That's for the radio part. If you look at the wavelength, we are looking at 20 gigahertz up to roughly 100 gigahertz. On the other side of the spectrum, UV bands, so observed from GALEX, there was also a claim from Henry et al. That there is an excess not understood in the UV wavelength, especially at high galactic latitude. So the UV is actually interesting because there are not so many UV sources in the galaxy. You have the young bright stars, that's one, and that's pretty much it. And if you want to model the UV map of the galaxy, you would have to calculate precisely how the UV radiation is scattered, deflected, and absorbed as it travels across the galaxy. The optical length of the UV is much, much shorter than the optical length for radio. Basically, radio, you see the galactic center. UV, essentially, direct UV, you see only the close surrounding within a few hundred parsecs. That's it. So why is it interesting for us? Because again, you can do this calculation with the AQN. The process is simple, I showed you before. All you need to know is the distribution of dark matter, distribution of baryons, the delta V between the two species, done. You can pretty much predict anything. So this plot is showing you the flux from AQN that I showed you before, again, across all these frequencies. But now you should pay attention to the shape of because it's prime traveling emission, so it's exponential cutoff with a hard spectrum in the radio. Look at the shape of those things. And I'm showing you 3 shapes for 3 different AQN temperature. 0.01 EV up to 1 EV, typical temperature expected in a galactic environment. That's something I said before. The WMAP bands are right here. And in fact, practically, it's very easy to explain the WMAP haze in the context of AQN. Very easy. You just fit a flux to all these bands right here, and you get some number out. But once you've done that, the AQN physics is absolutely rigid, fixed. You cannot change it. In particular, if you fix the model from, say, radio wavelength, you cannot adjust anything on the UV side of the spectrum because it's Strahlung emission again. And that's where it's interesting to compare to this UV excess that people claim exists. Because as you can see, potentially we could have a double detection here of this effect by combining radio to UV. It's still work in progress. Again, what's difficult is not much the radio part. Like I said, the radio part is easy. What's difficult is to produce a UV map of the galaxy that comes from the immediate surrounding of us. So you need to know the dust distribution within 1,000 parsecs or so in 3 dimensions, right? Because the dark matter travels in 3 dimensions, so there is such a map recently produced from Gaia and from dust. So they try to reconstruct the dust in 3D, so there is such a map that shows the dust distribution in 3 dimensions around us within a volume of roughly a few hundred parsecs on each side. So hopefully we will have some data points somewhere here soon. So I'm almost done here. I want to finish saying that, I mentioned all these effects, but there is a lot more and a lot more papers. We published many more papers in our group that look at different astrophysical environments. It doesn't have to be only cosmology or galactic physics. In fact, again, the model is pretty simple. Once you have the basic recipe, applying it to different astrophysical contexts is easy. So this is just a list of things we looked at. We looked at the impact of antimatter nuggets falling on the sun. We look at them as potential explanation for fast radio bursts. We looked at what happens when those antimatter nuggets cross the Earth. Could we detect them anyway? What about the X-ray background around Earth, which again, something weird has been detected with XMM. So there is a list, it's not a complete list of things here. So I want to finish, state again this, I'm not trying to sell you a model here, just to be clear, I'm not a salesperson. My main message, if there is one message I'm asking you to keep in mind, is why it's difficult to prove the nature of dark matter, maybe because we are not looking at the right thing at the right place. That's the main thing, because the so-called dark matter paradigm, which is taken as granted, as the basics, the mother of everything, it's not based on observations. It comes with assumptions, hypotheses, which are just assumptions and hypotheses. So what comes next for us? Of course, personally, I'm interested in pushing the research around this direction. What's interesting for us, things we have in mind, and it's somehow a call for collaboration, people doing hydro simulations in complex astrophysical environment. I'm interested talking to you because I would like to apply this basic recipe to the simulations you do, see if there is anything we could predict could be detectable. In particular, H2 regions are interesting because, like I said, the nuggets, as soon as they get heated a bit, they will get ionized. So you may say, well, you have ionized dark matter, charged dark matter, so it will generate magnetic field and so on, but it does not, because the thing is, they are extremely massive. So the Larmor radius, the typical curvature trajectory of a charged particle moving in a magnetic field is extremely large because they are so massive. So they will not follow magnetic lines. They just keep traveling in straight line almost. However, what charged dark matter can do, if it's so massive, it can generate an electrical field, magnetic field from DC current. So you have potential for generating maybe primordial magnetic fields from charged dark matter. For H2 region, if you have charged nuggets, they will, of course, so antimatter ones, they are negatively charged because it's antiquarks. So their effective cross-section, because of Coulomb force, will be much larger than if they were traveling in a neutral environment. Because of that, the annihilation with the surrounding protons, the annihilation rate, collision rate will be much higher. So potentially, we could see some dramatic effect here, which may invalidate the model or maybe be consistent. There is a potential source of positrons in the galaxy as well, because those positrons that leave the system, where do they go? So it also in the context of AQN, you have potentially a source for positrons, and positrons has been historically and also in galactic physics. Yeah, I think that pretty much said everything. So I will stop here and take questions. Thank you.
Thanks a lot. So we have a first question already here.
Very interesting, Ludo. You know what the answer to the question you're asking about why we're looking where we're looking? It's because you know the story about the guy who's lost his keys, and you're asking him, why do you look in the dark next to the light? Because that's where you can see. But I think it's a bit it's very interesting, but it's a bit disingenuous at the start when you talk about trying to prove that dark matter is dark. And so you can't prove anything. I mean, you can only find observations which show that it's false. So I guess these particles are too massive to have any kind of signature in accelerator physics. Is there any signature you would expect in at CERN that could give evidence with these kinds of particles? They're too dense.
No, because the number density would be way too low. So even ice cube would not detect any of these things if they have a mass of a kilo or more. The chance for detecting them in ice cube is basically 0 over a couple of centuries. So you will have to wait a long time.
So while I run for the microphone, Cedric, you had a question on internet. Can you speak up?
Yeah. Yes. Can you hear me?
Of course.
Yes. Hi, Ludovic. Thanks very much for the nice talk. Yeah, I had a question about nucleosynthesis. So what happens? I mean, the interaction between the nuggets and the what matter at nucleosynthesis time could potentially, I guess, change the nucleosynthesis. No.
It does not change nucleosynthesis. It does generate. Basically, you would have annihilation of light nuggets. So they would turn into photons. So they will just add up to the budget of photons, essentially.
But it will not inject energy sufficiently enough so that the nucleosynthesis will change.
No.
Oh, okay. Thank you.
Thank you, Ludo, for this great talk. Very eye-opening. So I have a troublemaker question. When you show your equations with the calculating the emissivity as a function of the number density, and then you the cross-section velocities. The cross-section might depend on the velocities, so as it often does. So could one imagine that the typical velocities of protons entering these nuggets are so high that they don't have time to interact? So that would effectively reduce the cross-section. I'm sure people have looked at this.
It's the cross-section I used for the nuggets calculations is the geometrical cross-section. So it cannot get anywhere below that. It can get bigger if you have charged nuggets.
But can't you imagine that if you go right through very fast, you might not have time to interact?
If it goes through, it does interact because it just cannot go across the nugget, the proton, right? You're talking about the proton. It could be reflected. Quantum reflection, that could happen, yes. But going through, no chance. It's just nuclear density.
Yeah,
so
it's like billiard balls.
Yeah.
Yeah. Okay.
Nikos?
Okay, nice talk. Thanks, Ludo. My question concerns the amount of those nuggets, the mass. You're trying to put basically all the dark matter in the form of those nuggets, okay? Which means 5 times the number of baryons that are used in primordial nucleosynthesis. So the question is, what determines this amount? Why should all the quarks basically at that time get into the form of this very heavy configuration? And what determines why just 1/6 remains later in the form of free nucleons. Usually when you get out of nuclear equilibrium, it's lighter particles that are favored. For instance, before nucleosynthesis, you have 6 protons for every neutron. And because they're lighter, that's why. And in that case, I don't know very well the quark-hadron phase transition, but as you said, it's normal physics, standard model. There is nothing special there. So why such heavy configuration comes out favored by that?
It's almost normal standard physics, standard model physics. You need the action. Without the action, you don't have any of this. So the action is what triggers the formation of those nuggets, and they grow until they reach their mass, until there is basically no more matter and antimatter to accrete. But
so why are there these nucleons left? These free nucleons, why are they left? Why such 1/6 of the quarks remains free? And why doesn't all the matter goes to the
yeah, so why 1/6 and not 1/7 or 1/3 or that is just pure statistics. In a way, no, because the dark matter in that case is coming from normal matter. So what you have, so I did not mention I have a brain fart here. Baryogenesis, yes. I did not mention baryogenesis. At the quark-hadron phase transition, you have still all your baryons and antibaryons. You have all your quarks, all your antiquarks in equal amount. And what that process is doing is that it generates a hierarchy of objects, antimatter nuggets, say for 3 units, matter nuggets for 2 units, and the rest is us. So you have 3 units of normal matter, 3 units of antimatter. And why is it 3-to-1 and not 4-1-1, or is just an order 1 parameter, which I find a lot more satisfactory than a fine-tuning, where you would have to fine-tune things 10-10 or things like that. So there is no well, actually, that's not even true. In principle, you could calculate why it's 3-to-1. But that would require solving QCD completely, which nobody knows how to do this. Yes. But it's an assumption that's satisfactory in the sense that you don't need anything else to explain baryogenesis.
There are other questions. I will shortly abuse my chairman privilege and ask a question following this one on the nature of this action field that you need to generate those nuggets. So there are perspectives to measure the existence of action fields in the future CMB experiments such as S4. Do you know how much this particular field and the property on this field will be tested by S4?
I think the action you are talking about is ULA, ultralight actions. Yeah. So they have nothing to do with this.
Okay.
So for this to work, you need the QCD action. The ULA is a very strange beast in a way. It's an action, yes, but it's not a QCD action. In a way, you have to change its coupling so that it doesn't overclose the universe. The reason why the normal QCD action cannot be ultralight is because if it were, there would be too much dark matter. You would have so much action everywhere, they would overclose the dark matter. It's the lower bound for action mass, actually, which is about 10⁻⁶ eV. Okay. So anything below that is beyond QCD action. And ULA 10⁻20 eV, 10⁻18 eV we are talking about is a completely different beast. It carries the same name, but it's completely different beast. Okay. In particular, ULA do not solve the QCD CP problem, strong CP problem. It cannot.
So there was a question from Michel remotely, then we'll go here. So Michel, can you speak up?
Yeah, hello. I have a simple basic question, maybe slightly aside. When you have dark matter and anti-dark matter nuggets, would that help to explain why the antimatter has disappeared and only matter remains? And if yes, how?
Yes, this was my answer to Nicola, that you have for free an explanation for baryogenesis. So yes, absolutely.
Okay, thank you.
Hi, thank you very much for the talk. Some of my questions are already answered, especially about the effect of axion and coupling of axion to these particles. But I wanted to know, because you are considering that they are antimatters, at the very early universe, they cannot be, I mean, have you tried to see if they will not be annihilated partially or other way around? The normal matter would be annihilated by this nugget because at the very early time, the cross section would be much higher because of the higher, much higher densities.
Yeah. So I think again it goes to my answer to Nicolas. You have a process where just when the quark hadron phase transition takes place, you have equal amount of matter and antimatter. The existence of axion triggers the formation of those nuggets, but in an asymmetric way, because axion does not couple symmetrically to its a chiral field, does not couple symmetrically to matter and antimatter. So you have a leftover of things that does not grow as nuggets. We call this matter, we call this us essentially. But you have a massive amount of annihilation that's still taking place. Yes, you still have normal annihilation that is in conventional cosmology, but you also have this nugget formation that's taking place in parallel. And you also have a disparition of light nuggets because of annihilation with the ultra dense, maybe that's your question as well, ultra dense baryons around, they will basically completely destroy the small mass nuggets.
Yes, and also you have to consider also not only baryons, but also leptons, because we see that the number of leptons and baryons in the universe are roughly the same. Therefore, we should, I mean, whatever process that you consider for the formation of these particles, it must also explain why what we see as matter, number of baryons and number of leptons are roughly the same.
Yeah, for the leptons, I don't know. But yes, that's a good point.
I have another, no, Luc has no more question. So is there any other question in the room? There was a question from Norma. Norma, can you speak up, please?
Yes, good morning, thank you. I placed it, I think, in the discussion. The point of all this, Ludovic, is that the constraint for dark matter is not only from the density of dark matter, say the space density, but also from phase space density, namely the velocities. And doing that, it appears very clear that the mass of the dark matter particles, whatever the type of the model of the particle, should be at the kilo electron volt, of the order of the kilo electron volt, namely from 1 to 10 kilo electron volt for the thermal relics, for instance. And then the action is excluded, the action, whatever Bose-Einstein condensate, is excluded by more than 17 order of magnitudes. And this appears from very strong constraints, and Gaia and Gilmore have given, I mean, the last ones, and that is a very, I mean, a very strong constraint placed on the nature of dark matter particles, which, by the way, as you very well explained it at the beginning, the WIMPs are also excluded by the same reason. And so this is the point. We should look at the right direction, and the right directions are the kilo electron volt masses. And from the density that was not mentioned here, the central density, namely the profiles of the dark matters in the galaxies, etc., it appears also as a strong constraint on the statistics of the dark matter particle. The statistic cannot be boson, but fermion. This is explained from the quantum pressure. So this is my comment and my point to this. Also, it's very interesting what you mentioned about the distortions on the CMB spectrum. And this Alan Cowood mentioned very in the, 10 years ago, very clear that is the kilo electron volt particle that could give the right measure signatures for that. So thank you very much.
Can I comment on that?
Yeah, of course.
So for the KEV search for dark matter is, of course, should be pursued, but it's in the context of thermal production of dark matter. And AQNs are totally not thermally produced. So I think keeping the search for...
Yes, but the misalignment scenario, which is the most canonical for actions and so on. We did with Hector de Vega for non-thermal equilibrium too. And this is monthly notice of Royal Society in, in 2010. So it's 10 years ago, say. You can look for that and many other work. So it's real. It's seriously. From this, we already many years also pointed out that WIMPs cannot be the dark matter, and this appear true. And the same way why supersymmetry is not found at the Hadron Collider. There are explanations for that. And so, because you are right in the sense that we need to look at the right direction, I pointed this to you because all your searches for distortion, is very interesting, but take the right particles, whatever the model would be. The important thing is fermions and the mass of the particle. And more than that, the electromagnetic signatures appear very naturally from the decay of the particles, just Feynman loops. These particles decay from the quantum mechanically way, and that is the way in which you can find signatures. And now, Ice Cube, I have the last results, and in the decay of particles from neutrinos, it's very interesting. It's really very interesting, and so I don't know what will be the real dark matter particle, if there are neutrinos or another one, but it should be a fermion and in the kilo electron volt order of mass.
Norma, I think there's a lot of debate here, so perhaps this is something you should have with Ludovic offline. There was perhaps another question, yes, from Cedric, which will be the last one. So please, Cedric, speak up.
Yes, thank you. Yeah, I had a question about the cosmic radio background that you discussed, Ludovic. So if I recall correctly, there is a idea that there should be a cutoff at low frequency due to interaction with the intergalactic, maybe plasma or something like that on this background. So this is not observed in the data, or?
I don't think I understand your question. So frequency for the AQN, you mean?
So I thought that the cosmic, if you look at the cosmic, at the lowest frequency of the cosmic background in radio, right? Which I guess the plot you showed, no? I saw there was a cutoff. Supposed to be a cutoff due to the interaction with the intergalactic or interstellar plasma. Yeah, at this lowest frequency here. And
cutoff.
Yeah, basically the sky becomes opaque at the low frequency because radio waves interact with the plasma around.
Oh, you mean the plasma cutoff?
Right. Yes.
By the waves.
Yeah.
No, it's much lower frequency as far as I remember. So that could travel. So the only objection people have, that will take us maybe a bit longer discussion here. The only objection people have against having this excess existing at high redshift is some apparent inconsistency with the global 21 centimeter absorption at redshift 15, 17. which the EDGES experiment claimed to have measured, if you have this radio background pre-existing at higher redshift, you should expect a massive absorption. And in the context of AQN, there is actually a way to prevent this. I did not talk at all about that because this is work in progress or about to be in progress. You have these X-ray photons that also are byproduct of interaction AQN with protons, and those X-ray photons could reheat the matter and precisely prevents this issue with absorption to happen. So you could have this radio background existing at higher redshift, pre-existing this redshift 17, 15, and not be in conflict with the absorption people have measured. The cutoff, I'm not sure. I think the cutoff is at much higher redshift.
Much higher redshift, you mean? Yeah. Because I saw the cutoff was at low redshift somehow. That's due to just absorption by the media around the Earth, basically, or.
So again, I think this is a question that you'll have to sort out offline. Thanks a lot to everyone for the questions. Thanks a lot for Ludovic. It was very interesting talks. And please, Pierre, next week, what do we have? What do we have next week? I forgot who it is. So come back next week. Thanks a lot. Bye-bye.